My first question was to essentially create all of the infrastructure for the Caesar cipher, but to use a shift of 0. So you could test that you recovered your original message because you wouldn't be shifting anywhere in the alphabet. This code looks very like my original example. There is basically only one change. So as a reminder from the example, we move through the message, all of the indexes in the message, index from 0 to length of message. For a particular index, so say an index of 0, we look up the character from experience is the teacher of all things at that index. So we look up, when index is 0, we get E. Letter in message is now E. Now we go to letter in message and we say, okay, in alphabet, in A, B, C, D, E, what is the location, the index of E? And it's 0, 1, 2, 3, 4. So then what do we do? Well, for the null Caesar cipher, where we don't have any shift, we don't want to do anything. We want to just keep the index to be the same as it was. E was 4. We don't want to change it because we want to print the location, the letter at location 4 in the alphabet to screen. We include our special if then else statement to deal with spaces. But now here's the difference. When we were looking at the alphabet example in the previous session, we would show the index to screen. So we would have shown E, and then we would have shown 4, or 5 if you added 1 to it. But we don't want to show the index. We want to show the character from alphabet at that index. So you've seen this statement before. It looks just like the character from message at a particular location. So an index 4, the character from message is 0, 1, 2, 3, 4, which is R. But at index 4, the character from alphabet is 0, 1, 2, 3, 4, E. So one more time. This should be very familiar to you at this point. We've looped through the indexes of each letter. We've recovered the letter. We've looked up the letter in alphabet to get the index that corresponds to E. We haven't shifted it at all. The shift is 0, so we stay at E. And then crucially, the new element, we display the character from alphabet at that location, at location 4. For X, as we're looping through next, index of 1, at index 1, the character from message is X. Where is X in alphabet? Well, it would be at location 23. We're not going to do anything to location 23, and we're going to show the character from alphabet at location 23, which is X. So the trick here was to reuse this block, but to use it in alphabet at a particular index in the alphabet rather than using it on message. So if we've got this right, we should see the original message. We haven't shifted anything. We've done a lot, but in doing a lot, nothing has changed. So the reason to do this was to check that your method was working, so that when we implement a real shift, we know it is working. Here's the next block of code. By the way, it's identical to the first block of code. The only line that has changed is change index in alphabet. And now instead of changing it by 0, we're changing it by 3. Only change, one line of code. And you get your encoded message. The reason you can tell it's working is, well, here's one way to tell. Let's put an A at the start. We know that for the Caesar cipher with a shift of 3, the one Julius Caesar himself used, A should become D. We also know that E should become H. So this is just a check. By adding an A space in message, we should find we get D space H if we've got this right. D space H, and then so on. So now we've got that. Let's delete the A, remove it completely, and see what our message is. It's H space SHULH, And hopefully you wrote this down, but if you didn't, I wrote the answer down for you. It looks like this. So this is the encoded version of experience as the teacher of all things with using a Caesar cipher with a shift of 3, a key of +3. So think about this first translated encoded word, hash-ul, it starts, has, H-U-L. Let's see if that's what we actually have. Space, S-H-U-L. One more time, we should get hash-ul. We get H space S-H-U-L. Why is that? Well, the E with a shift of 3 in the alphabet, E, F, G, H becomes H. The P with a shift of 3, P, Q, R, S becomes S. So that's the H and S in the first hash in hash-ul. Why is the X missing though? It became a space. Well, let's go to X and move 3 places to the right in our variable alphabet. X, Y is 1, Z is 2, O. We're off the end of alphabet. Your microbit doesn't know what character is off the end of alphabet, so it's using a space to display the X. X is the problematic letter for this reason, H space S. So how could we fix this in a fairly simple manner to instead display the X as its encoded letter? Well, one way is to expand your alphabet string to allow it to wrap around. So now E will go to H as before, but look what happens when we have X. We'll go to Y, to Z, and to A. So just by adding ABC on the end of the alphabet string here, we've given X the space to loop around and become the A we expect in the hash-ul start to experience. No other change, just added ABC on set alphabet 2. Let's try that. There we go. There's our secret message in all its glory. If you got this far, fantastic and well done. You have now written serious code to create cryptic messages, create secret messages in a way that a great leader in military history used to use to cipher his messages so that they couldn't be easily read. But obviously, the real interest with secret messages is to be able to decipher them. And my stretch goal, if you got to it, was to try and take the message you got from this piece of code and to decipher it to recover your original message. So crack the code. Well, here's an example of how to do that. Here, trust me, let me just elevate this even further so it's the starting block. Here is the secret message encoded by the Caesar cipher. Experience is the teacher of all things, we know the answer, but with all the letters shifted 3 places to the right. I've only made 2 changes to this code. One is, just like I added ABC to allow my alphabet to wrap around to the right, I've added X, Y, Z, so that any characters we're translating here back into X can wrap around to the left. So the X, when we did the Caesar cipher, became 1, 2, 3, A. When we go in the other direction, we're going to want to allow the A to go 1, 2, 3, and become X. That's one change, very small. What's the second change? Very simple, I hope. Our key to encode the message was 3. Our shift to decode the message, to decipher it, our shift to the left, is just -3. So with that one change, you could take the secret message, hash-ul hakafa lev wicke wudefike redo wicke, and turn it back in to the original message. And let's check that works. And we get experience, and so on, is the teacher of all things. If you made it this far, congratulations. You can now decipher messages written in the Caesar cipher. Tomorrow, I'm going to give you an arbitrary message, not an arbitrary message, one that I've encoded using the Caesar cipher. And your goal is going to be to try and decode it and see what the secret message is actually saying.